All right, so hello everyone. Welcome to episode 67 of Warsaw Quantum Computing Group Meetup. My name is Paweł and I will be the host and moderator today. Today we have pleasure to host our great speaker, Professor Zbigniew Puchała, and he will give a talk titled Integrating Quantum Optimization and Classical Heuristics for Airline Fleet Scheduling. Sounds interesting. Before we start, just a few announcements. So as you can see, this meeting is recorded. Later the video will be available on our YouTube channel, hopefully. If you have any questions, so first of all, there will be a dedicated Q&A session at the end. So you can always ask your questions at the end. But if there are some urgent questions, you can also raise your hand or post your question on the chat, and we can try to interrupt and ask a question on the fly. Okay, yes, before we start, we would like to thank our partners, our strategic partners, for supporting us and helping us in organizing the events. Quantum.io, the main partner today, Sanover R&D, Onyx, Cogit, QLab, and ThinQubit. We'd also like to thank our honorary partners. There are plenty of them, as you can see. They also help us in advertising the events. Okay, so let's officially start the talk. So, Professor, if you are ready, we can start. The Zoom is yours. And first of all, thank you for accepting our invitation. It's our pleasure to have you with us for the first time. And we can start.
Yes, thanks a lot. Can you see my screen?
Yes, I can see your slides.
Okay, good. So good afternoon, everyone. Thank you for joining this session, and thanks for invitation for this meeting, this seminar. So today I will say a few words about what we are doing at the Quantum Z company, which is related to disruption management and scheduling for airline industries. This lecture is a bit technical in nature, so it is actually some engineering stuff we are working on, and we are doing a lot of classical optimization, but as well we are performing some quantum-inspired algorithms and some quantum, like we are also using some quantum computers to make some kind of calculations. So it will be technical, and that's just the information at the beginning. So actually the work is we use a quantum-inspired approach to the problems of airlines and that the airline companies are dealing with. So especially we use classical methods derived from classical operational research, some clever heuristics for the problem of disruption management and scheduling. But I will say also about something related to quantum computing. So we combine these classical techniques combine classical techniques with quantum to solve some smaller problems related to the scheduling and disruption management. And later on, I will say something about one sub-problem, namely tail assignment problem, which is just one of the many problems we are dealing with when preparing the solution. Okay, so it is important to note that the airlines operate in highly competitive and dynamic environments. So there are tight margins, high customers' expectations, and actually real-time disruptions make scheduling a very difficult task. Sometimes we need a solution within minutes, but the problems itself which we want to solve is usually huge, and it is difficult to obtain an optimal or even close to optimal solution with reasonable time. So we are actually building such a solver. And some of these subroutines are, we try to make them to utilize some quantum information procedures. So I will go through it in later. But what is important that companies, so the airline companies needs to have, first of all, well-designed schedule, so which is robust with respect to potential problems. What I mean robust is that it's can be easily fixed or some, let's say, disruptions like delays does not cause too many problems. And on the other hand, when we have this design schedule, we want to have a method, an algorithm to reschedule when the disruptions occur, because it usually happens, and it does happen that disruptions occur very often. So we must have a way to do this in such a way that we want to have, let's say, minimal costs. The cost is itself is how to define the cost for this kind of operation is a difficult task itself, because there are some hidden costs related to, let's say, passenger satisfactions, which came up like in long term, but there are of course some direct costs related to actually that the company needs to pay some compensation or must pay some other things related to hiring to booking another airplane or so on. As you can see on the slide, I have put some information. So poor scheduling can lead to cascading delays, missed maintenance. This is a very important thing, because maintenance is actually something when it is not done at a given time, the plane itself is grounded, so it cannot operate. And of course, we need to take care about the passengers itself. The schedule itself should be robust, as I said, so it should tolerate a minor disruption without major problems, and it should be flexible, so it can be easy to fix. And I mentioned before concerning this cost minimization, which we are dealing with, so direct costs and indirect costs related to this satisfaction. Okay. And why quantum computing? Well, quantum computing seems to be promising when we are dealing with complex combinatorial optimization problems. When the quantum computer will be mature enough, I believe that they will be useful in this case, and they will somehow its potential will be utilized. So, but it is also important that the real world scenarios will require some kind of hybrid approach, where the classical quantum methods will work together. And actually, this is what we are doing. So we are building a classical solver for problems, for a set of problems related to airline scheduling and disruption management, and only some subroutines utilizes the potential promise of quantum computations. So this is things we are doing. Overview of disruption management in airlines. So disruptions like delays, cancellation, or maintenance issues are handled by airline companies daily. So the crucial aspect of this is, no matter how good the original plan is, it will sooner or later, or rather sooner, the events will turn that you will have to reschedule it, because there will be some kind of delay or some kind of problem related, for example, because of the weather or technical failures or any other problems which can appear. And what is important to note that in practice, most airlines today rely on highly manual process for this management. This is a bit surprising, because this is very crucial for its functional, how they function. So actually, there are these operation managers, which they have some kind of software which helps them a bit with decision making, but most of this is human driven. So the people there assess the situation. They look at what aircrafts are available. They evaluate all other things like gate, our crew constraints, and they actually try to make the best judgments in the real time based on their knowledge. So actually, these control centers must work 24 hours a day, and when something bad happens, like flight is delayed, or let's say the crew duty is out of date because, for example, pilot can work for a specific number of hours and later he must take a rest. So if this delay is like substantial, then there's no possibility of flying because of the crew unavailability. So there are a lot of these things to be taken care of. So that's why this problems is actually difficult. The other thing is manual coordination between departments. So the things related to crew scheduling, maintenance, and operations, actually, they are usually taken care by different departments, and it is difficult to, let's say, have in mind when rescheduling things, what's going on in all of these departments to have them working like to have a global solution which takes care about all of these constraints. So there's this kind of problems do occur. So there are a lot of limitations, so manual process can be time consuming. We have insufficient resource utilizations, and of course another very like bad things can happen. So limitations are like quite big. So first, the methods that the companies are using right now don't scale well in large network with, let's say, hundreds of aircrafts and thousands of flights, and local fixes can introduce some global effects that aren't seen at the beginning. And the recovery option tends to be narrow because the system wasn't optimized at front. And the current systems actually don't support integrated decision making. So as I said before, maintenance, scheduling, crew assignments, gate planning, and this kind of things are often managed separately. So when the disruption occurs, it's hard to account all constraints at the same time. And this leads to suboptimal choices. So this is actually why we design integrated optimization tool, which enable, let's say, mostly classical operation, but also hybrid methods related to quantum. And we actually anticipate common disruption and build flexibility into initial plan. And then the need for the, let's say, ad hoc fixes will drop significantly. And when the disruptions happen, we'll have more structure and scalable methods to recover. Okay, so this was just the beginning. So from practice to principle, what we are working on is trying to build solver-based optimization approach because of these limitations. So because today's planning tools are mostly based on rule-based systems built for specific scenarios. So what is actually the problem? For example, adding new rule, like let's say requiring that every plane should return home every 3 days often means that the algorithm, you have to change and rewrite the underlying algorithm. So this is slow and actually hard to scale. The root issue is tight coupling. Business rules and optimization logic are deeply connected. Any change in business needs, like new maintenance requirements or updated airport regulations, will force developers to modify the code. So that's actually the problems which can happen. So what is actually the alternative? The alternative, besides this hard coding, is to prepare some kind of solver-based approach. And so the business rules are defined in this solver, and actually most of this is as a parameters of the solver. It's not hard-coded, but this it can be defined on some just changing few lines of codes can modify these rules, and the solver will accept them and will work smoothly from them. And what are the benefits for this kind of task? So first of all, flexibility. So constraints and objectives can be added in a single configuration file. Example I said before, just one line of code when we want to have some fixed changed. And this is the first thing related to the flexibility of this kind of solution. Transparency, so it is easier to audit and understand the decision making. And debugging becomes straightforward. So models are easy to interpret and audit. And modularity, we can use the same solver framework for different problems. Tail assignment, crew pairing, gate scheduling, etc. And so it actually encourages the innovation and reduces the long-term cost. The problem with this kind of integrated solver that it usually, because the problem itself is huge, it usually the underlying problem to be solved, so this mathematical problem, optimization problem, can be quite huge. So it is not enough to use methods from operational research, which are actually, there exist methods, but the problem is that they grow pretty quickly, and it is sometimes impossible to execute and have them run in the given specific time. So that's the problem we encounter. So first thing we consider some heuristics, and of course we also consider the usage of quantum-inspired approaches in hope that in near future we will have access to a working quantum computer that will enable us to solve this kind of problems quickly. So where the quantum enters, so hybrid quantum classical solvers are well suited for combinatorial problems. So if let's say the quantum computers will be ready for this, then we can just run them. At the moment, we are using for testing purposes. Sometimes we use a quantum computer, but mostly we use a simulator of quantum computer for solving the problems we are dealing with. Okay. So this is actually what we are working on. So we are working on Airline integrated recovery system. This is one task. The other task is robust scheduling, which is very related. One is related to the other, because this recovery system as an input, it would be the best if it have like a good robust schedule at the beginning, so then it is easier to recover it. And modular solver-based platform for disruption recovery in airline operations. So this airline integrated recovery system supports real-time decision, and it's using hybrid classical quantum methods. But as I said before, we don't have at the moment, let's say, a real advantage with the use of this quantum methods, because as you all know, we don't have quantum supremacy or quantum advantage, but the solvers which we are using, which simulates quantum computers, actually works pretty good, and we are able to, using this quantum inspired algorithms, to obtain similar time to solution as classical optimization tools from operational research. And this airline integrated recovery system is built for flexibility, robustness, and feature scalability. So this is just a sketch of what we are doing. So the airline will introduce some kind of disruptions to the center which takes care about them. Our system will obtain a solution request, so we have a limited time. In case of disruption management, we have very limited time for the solution, because usually it should be within minutes, because the decision which flight to be canceled, which one to be delayed, and what should be swapped, for example, should be done within minutes, and we obtain this solution provided, and the operational center actually provides instructions. So what are the inputs, just to that you can see the scale of the operation? So we need flight schedules as an input, aircraft data, operational events, and environmental constraints. And all of this is standardized and defined in the actually API of the solvers. So as you can see from this, maybe someone who has done a bit in operational research or optimization see that the amount of data when the schedule is big, when the schedule uses many resources, is like huge. So the modeling layer, so we have declarative modeling of rules and objectives. We have constraints to be encoded in configuration files. So this is also an important thing, that it's not that it is hard-coded. And the key features that are easy to adjust for business rules, and support soft constraints, and enables multi-objective optimization. So solver actually can work on many, let's say, we can use many engines when we want to have a solution. So classical solvers, like for solving mixed integer programming, like Gurobi. We can have quantum inspired solvers, and hybrid solvers like D-Wave. So what we are doing is we use a bit of mixed integer programming together with heuristics, because it is very difficult to obtain a solution at the reasonable time using only mixed integer programming. But we also try to some of the subroutines encode in quantum procedures, and that's how we actually utilize this potential of quantum computation. Okay, and so after this, our solution performs, we perform some post-processing. So this is just technical things. So repair minor impossibilities, align output across fleet, crew, and maintenance, and generate visual reports and ready to use. So it is just important to stress that the number of variables, I didn't put it here everything, but the number of variables in our case is huge. This is just, it depends on the data we are working with. So we have managed to have a collaboration with LOT company. So they provide us with their data, and we are testing and using their data to improve the solution. And even the LOT is not a huge airline company, but still with the number of planes and the number of flights they have and the restrictions related to the crew availability, the maintenance, and all other things which are there, it turns out that classical solution based purely on operational research is not giving us results in reasonable time. Okay, so this our solution actually provides an interactive dashboard for planners. So this is just the technical things. Maybe it is not interested for this audience, but this is what I just want to mention, that what we are working on, how this is this quantum actually subroutines is a part of a very large system which uses like the whole optimization for this recovery system, and we obtain visual tail assignments, timelines, real-time conflicts, alerts, and solutions. What if scenario analysis? So actually, like simulation steps for what will happen if another disruption occur, and one can manually override live solver returns, live solver reruns. Okay, so this was just oh, I see there is something on chat. Probably analog classical electronic with certain level of state can account for the problems. Yeah, probably so. So thanks for this message. So this was just to have a brief what actually we are doing while working on this approach. Now I will focus on just what is a tile assignment problem. This is one of the sub-problems to be solved. The tail is just a name for a specific aircraft. So we have, let's say there are types of planes, so like Boeing with a specific number or Airbus and so on, but the tail is a specific plane with a specific number. So it is important to, at some stage, assign a plane for a specific flight. Either this problem occurs either when we do scheduling for some future operations, either if we're doing for rescheduling, when disruptions occur, we need to reschedule our original schedule. So we need to make some changes, and one step of it is to assign specific planes to specific flights over some horizon. Of course, there must satisfy some kind of constraints. The first one, maybe I think the most important one, is related to maintenance, because each plane has to have maintenance after a given number of flights. Otherwise, it cannot function. There are some airport rules, time windows, and there are this kind of constraints. And this is a very hard problem, and because there are like exponentially, it is exponentially, the number of variables grows exponentially with the number of planes. So it is hard. It can be solved easily for limited number of planes, but mostly we have to use heuristics for solving this, or in this case, when I will be talking about using some kind of quantum-inspired quantum algorithms. So there are methods for solving this tail assignment problem using integer linear programming, so binary variables for class constraints, and objective is, of course, to satisfy these constraints and minimize a cost related to fuel, potential delays, and maintenance. And of course, it is used by airline companies to make this assignment. Heuristic methods, there are some heuristic methods, so greedy search, local optimization, simulating annealing, taboo search, genetic algorithms. So there are plenty of possibilities how to find this solution. Usually it is fast scalable, but suboptimal. There are some strategies how to reduce the size of the problem, so divide it into smaller time windows and solve sequentially with continuity constraints and adaptable to real-time changes. So there are a lot of strategies how to solve this problem, because it is quite a popular problem in optimization task, and so there exists a way of doing it. So I will here say something about how to formulate this problem using Kubo. Kubo problems, I will explain them in a minute, can be solved using quantum computers. And what we did is encode this problem using as a Kubo problem and run it on quantum simulator and quantum computer itself to see how the solution behaves and is it optimal or suboptimal. And just once again, so goal is to assign each flight a specific aircraft or tail subject to constraints. And this is a subproblem of scheduling with high complexity. Okay, so what is Kubo? Actually, I don't know how our audience of this meeting is familiar with quantum information things, so I decided to put it here because it is somehow standard knowledge when someone is doing quantum computation things, but I will say it here anyway. So Kubo stands for quadratic unconstrained binary optimization. And it is mathematical, let's say, model of optimization used in many combinatorial optimization problems. It is quadratic, this is important things. And the goal is to minimize a quadratic function over binary variables. This is a general form of this problem. So X here is a vector of n binary numbers. Q is a given square matrix, n by n. And actually, we want to minimize this quadratic function, x transpose qx. This is a number. So we want to minimize it over all possibilities of 0 and 1 vectors. So this is a general form, as you can see, and as you can read it from the name, this is unconstrained, so we don't have any constraints here. The only constraint is that the entries are zeros or ones in this vector x, but there are no constraints related to, let's say, our optimization problem which we start with. So therefore, we must somehow impose the constraints which comes from the problem as a part of this matrix Q. And this is usually done by applying some penalties for not satisfying this these constraints. Kubo naturally fits binary decision problems like scheduling, routing, portfolio optimization, and it is used also in machine learning. And it is well suited for quantum annealers and quantum-inspired solvers. So actually that's why we use it. So actually we are using quantum computer, but a specific purpose quantum computer, namely quantum annealer. And we also use quantum-inspired solver, which we have actually built in at Quantum Z.io, which actually is performs even better than these quantum annealers, which are available now, like D-Wave. So actually, our quantum-inspired solver performs better than D-Wave, and we use it. We use sometimes for some, let's say, benchmarking for benchmarking cases. We use D-Wave, and sometimes we use our quantum-inspired solver because it actually performs better. So how do we solve Kubo in quantum annealers? So it is just to note, just to say that I said that we have built a solver which beats D-Wave, which is a quantum annealer. But there is like a promise in quantum computation, let's say, research area, that in, let's say, near future, this quantum devices will outperform classical computation, and therefore trying to encode some kind of problems into Kubo and to run them onto quantum computer. There is a promise that it will outperform classical solution and will have a benefit out of it. So that's what we are hoping for, that in near future we will be able to use a quantum computer in order to speed up our calculations and in order to have a solution for our problem fast. So on the quantum annealers, Kubo is mapped on the quantum annealers and Kubo variables. So this variable x, which consists of zeros and one vectors of zeros and ones, is mapped into qubits, and energy of qubit interactions encode the Kubo matrix. So there is a one-to-one correspondence between Kubo problem and Ising model, which is inside the D-Wave computer. And annealing process is actually gives us low energy, it transforms into low cost. Okay. And how this quantum annealers work? So we initialize a system in a ground state of a simple Hamiltonian and actually gradually change the system from this simple Hamiltonian to the one related to Kubo. So there's like a way of transforming this Kubo matrix into Hamiltonian, and we gradually change the simple Hamiltonian into this Kubo Hamiltonian. And at the end, we actually measure the final state to get a solution. So this is just a brief information how quantum annealing works. What are the limitations for practical use? So currently hardware is limited, so the number of qubits is limited, and the connectivity for quantum devices is also not full, so we need to have some kind of embedding. This is actually, I can say just that the solver which we have built at Quantum Z.io is not limited to these connectivity issues because we can solve fully connected qubits. Actually, hybrid solvers can combine classical processing, quantum solving, and classical post-processing to obtain the solution. So just to summarize, QUBO is a powerful formulation for hard optimization problems, and quantum computers, especially NERs, can solve QUBO models, and hybrid approach are practical and provide promising results. So the problem is that current annealers cannot directly solve large and dense problems. Therefore, many real-world solutions involve hybrid architectures where classical resources support the quantum component. Okay, so now there will be some technical things. I will briefly go through them because there is this a tail assignment problem, which we want to transform it somehow to QUBO formulation. So this is a bit simplified version. There are some things which are not present in this on this slide because it will be very technical, but I will just give you some idea about how we do it. So we have variables, and each one indicates that the tail T is assigned to flight F. So this is like indicator variable. So if 0, it doesn't mean that it is not assigned, and 1, it assigns. And constraints are encoded as quadratic penalty terms. So if we have some constraints related to this assignment, then we have to apply penalty. And cost function related to, for example, operational expenses is linear into objective. How do we construct the connection network? So for each tail, we construct a directed graph, and actually we denote some activities there. Edges represent feasible transitions. We have constraints such as turnaround times, because when, let's say, the plane has performed some kind of flight, then we need, after this flight, there must be some time from like legal stuff or even practical things that it cannot operate immediately after it. Okay, I see there is a question. By quantum-inspired solvers, do you mean tensor network methods or some other method? And also, does it happen that when the quantum-inspired method performs well, a classical non-quantum inspired method would surpass in terms of performance? Yes, that's true. Quantum-inspired solvers, we mean using tensor network. So actually, if you are interested in the solver which is designed at Quantum.io, you could find very interesting white paper for it on arXiv. And you can look to it, how actually we are doing it. So I will maybe when I finish the lecture, I will paste the link to the arXiv here on the chat. So thanks a lot for these questions. Edges represent feasible transitions. Constraints such turnaround times and airport restriction are embedded in illegal edges. So, for example, each flight must be assigned to exactly one tail, and we encode this as this kind of constraints. So we sum over all flights and sum over all tails and subtract one, and this is actually the penalty for this. And most of the other things we are using with similar mathematical tricks to perform. Penalize invalid flight assignments. So as you can see, there are a lot of this kind of constraints, which uses the summation of all possible tails, flights, and flights which are incompatible with flight with a given tail, because some flights may be incompatible with the flight if the flight requires like a huge number of passengers to be transported and the plane is small enough. For example, this is the simplest example, then the flight is incompatible with the tail. And we also panelize some intermediate connections. And as I said, this is a bit technical, so I don't want to go into details here, but there are many steps to be performed. And but there is a way to do it systematically, to design all of these constraints and to put them to this Cubo matrix, which we define at the end. The other thing is ensure maintenance. So there is another constraint here. So this is just another thing to take a look and penalize missing paths and so on. I just want to mention that this is not something which is ready, but we are working on and actually a paper describing this, and it will be available within a month or two on archive, and part of this will be there. So if someone would be interested in the details, then you will be able to find it soon on archive, how actually we are doing this the transformation to Kubo problem. And at the end, we have like operational costs as a linear function. So what is the message from this? The message is that there is quantum computers. They can perform different tasks. One of them, like for example, D-Wave computer is actually designed to perform one task optimization, which can be used for Cubo optimization. So what we are doing in order to utilize the promise of that the quantum computers will work and will provide us a solution in a faster than classical solution, is the way of transforming the combinatorial problems to this Cubo formulation. So we want to use a specific purpose machine like this D-Wave to solve a given problem. And this is actually what we've done. We are using, actually mostly we are using our solver, but this can also be run on D-Wave quantum computer to solve it. And finally, we have the full Cubo matrix here, which is related to constraints and to optimization things. So as I mentioned before, Cubo is unconstrained problem. That's why we have to impose the constraints, and actually we have to somehow consider the lambda parameters, which stands for the penalty for given constraints. Problem with this, as I mentioned before, these problems are large, and so is the Cubo formulation also is becoming, it grows quickly. So we cannot run away from this problem, since we are dealing with a huge amount of data, a huge amount of variables. Either this is a classical formulation or Cuba formulation. It turns out that it grows very quickly, and there are these hardware limitations for quantum computers. So we have to deal with it somehow. But still we can solve some, let's say, not very big problems using this method. So we can, of course, use some, let's say now, heuristic way of reducing the problem. So we can solve this tail assignment problem separately for each aircraft family. So if we decide that for a given flights, given aircraft family, aircraft type should operate on these flights, then actually we reduce the size of it. So this is like common way to come to this solution. So we separate actually the network of flights into smaller network of flights, and each of it should be operated by a aircraft from a given family. And this method simplifies the constraints and reduces substantially variable count, but it actually depends on the number of aircraft families which are available in the company itself. The other method is rolling horizon for tail assignment problems. So we break time horizon into smaller overlapping windows and solve sub-problems iteratively. But for this, we need to ensure the continuity because after this, when we have this overlapping windows, we need to have that the whole operation is continuous. So we don't, given plane cannot teleport from one airport to another. So there are discontinuity issues. It reduces complexity, but actually this, because of this reduction, the solution will probably not be optimal, but it will be, let's say, close to optimal. But as it is in this hard optimization problems, it is always difficult to find how far it is from optimal solution. But this kind of reductions are often used, and we also use them for this tail optimization problem. The other thing is because this is a unconstrained optimization, so there are these penalties related to not satisfying the constraints. It may turn out that the solution will take this penalty, and actually the constraint will not be satisfied. So we need sometimes to make a correction. So this is the problem which can occur when we trying to solve a constrained problem using unconstrained solver. So this is another thing which actually occur. Operational robustness. So another thing, just to mention what we are dealing it is when we are considering scheduling. This is a bit. It seems to be of what I said before, because this is like a general things we are considering not only for the Cuba formulation, but for robust scheduling, we need to consider buffer and slack time when we consider this when we consider building a schedule. So when we are doing this assignment of specific planes to specific flights, then one, we can use somehow optimal solution in terms of, let's say, the fuel we need to burn during the operation and some other things. But the other thing is to have it robust. So when we have a delay, we don't want to have that delay will spread across the whole network. So we want to include some buffer and slack time, and this is also included in our cost function. Okay, there is a question. So I'm not sure, would tab be embedded into Cuba? That shouldn't in principle reduce the complexity. Operation may be easier, but I don't see why the complexity will be reduced. The complexity of the problem will not be reduced. So actually the promise of the quantum computation is not that it will reduce the complexity of the problem itself. The promise is that even for a complex problem, we will have something like a fixed time to the solution. So the promise of this quantum annealing machines like D-Wave is that the optimization step is performed at a fixed time, no matter how big the problem is. So the problem itself still be complex and still be huge, but let's say that we are given a running machine which can this program can be embedded onto it. Then no matter how the larger the problem is, then it's still the quantum annealing procedure will make it that the time to solution is in fixed time. So this is the promise. So it's not reduction of complexity of the problem, is that even the complex problem can be solved in fixed time. This is the question. This is the answer for this. Okay, thank you for the question. Okay, so concerning, okay, there's another question. To what extent some quantum can be used for flight schedule problems? Use of quantum from classical. Well, at the moment, I'm not able to answer this question. I will have to take a look at it and
because I mean, this question was raised due to the fact that you are not relying on usage of Shor algorithm that solves NP problems in polynomial time, right? So you basically deal with a kind of stochastic determinism, which is present, right? So in a sense, I try to reduce the possible representation for this usage of analog electronics with certain level of stochasticity that can mimic the behavior of the flight schedule, right? Or there is another attempt to quantum mechanics, which is just known to me, which is due to, it's like presumption that there's emergence of quantum mechanics from classical physics, where you use certain type of noise correlations, and then you are coming out. So there is Nelson quantum mechanics. So in a sense, like the problems tackled by you somehow rely in a certain extent on Nelson quantum mechanics, at least some sort of types of methodology in this direction. At least it seems to me.
Yes, I think you are right. So yeah, thanks for this reference. I will take a look at it. And yeah, I think
By the way,
probably
how many NP problems? How many NP problems you have unresolved in the flight scheduling problem? There is like How many
Well,
problems use this to?
Well, actually, I cannot give you the number at the moment. Yeah, this is because it it actually depends on the formulation of the problem for the problem itself that we are dealing with. Because what we are trying to do in this project is to have the problem as close to reality as possible. So we don't actually deal with pure combinatorial mathematical problems which are known from literature, but we are actually working together with an airline company which provides us a specific constraints that occur and at their while they're operating. Actually, we can all write it down as mixed integer program. And this is actually the all we can do it at the first is how actually we started to doing it. But it turned out that this problem, this mixed integer program is so huge that we cannot solve it in a reasonable time. But I didn't make reductions to unknown problems and say that this is related to this certain problem and so on, because this was actually not our task. Our task is to find a solution which is even close to optimal. So we focused more on designing heuristics for these problems and to build something that is working. So sorry, I cannot answer this question for you.
All right, thank you. I'm sorry for the too large comments, maybe in the video of yeah. Thank you for your answer.
Okay, so actually, because I'm just out of what I was saying, so this is just things we are working concerning robust scheduling. This is another things which we are actually adding to our solution. So in order to have the schedule robust. And so the scalability is that these tail assignment complexity grows exponentially with number of flights and number of tails. Decomposition. So this decomposition is heuristics. Reducing the size, and we actually use hybrid solvers and actually quantum machines in these hybrid solutions to solve a small version of these problems. So implementation, so the penalty weights tuning is critical. This is the problem, as I said before, is this penalty is too low, then we can obtain the solution which doesn't satisfy the constraints at the beginning. Encoding logic constraints requires additional variables, and we can actually we use our solver, but also try to use D-Wave and also classical solvers like Gurobi. So just to summarize, this problem is this tail assignment problem is one of the many critical in airline operations, but as I said before, this is one of the many problems we are dealing with. We unfortunately we cannot have an optimal solution. We have only because of these reductions we have something which we believe this is close to optimal. We make a Cuba formulation for this problem, which gives us that it is quantum ready. And hybrid methods can bridge the current technology gaps. Okay, and actually that's it, what I wanted to say. So thanks for your attention. And if you have any additional questions, then please ask them now.
Thank you very much for a great presentation. Yes, there were some questions on the chat on the fly, and you've already answered that, so thanks for that. Do we have more questions? I see that someone has raised a hand. Lakshya, so you can unmute yourself and ask. Please.
Perfect. Am I audible?
Yes, we can hear you.
Thank you so much for the brilliant presentations. I just had a quick question on regarding the formalization. So, once you're doing a Kubo transformation, I believe there is no domain expansion, so you lose a lot of non-local correlation functions that are generally a part of the conversion. And second, how are you dealing with the variable chain strength while formalization of a system? Because inherently it's a classical to classical transformation, right? So all you get is a rho x, which is a probability distribution at the end.
Yes, so we need to, let's, I will begin with the second question. Concerning this transformation, because we need to at the end have everything in binary variables. Yes, so this is the problem, but we begin with the variables which usually are not binary. So we have this. This is the problem, but as I mentioned, so actually for this specific problem of tail assignment, we have the most of the variables are related to indicator variables related to the given flight is given by a specific plane, and the constraints actually are also as I mentioned, there is no problem with that. So actually, we don't have like a big problems with transformation of classical variables. And can you repeat the first question once again?
Yeah, it was regarding the chain strength once you convert it into a Kubo formalization. So essentially, all Kubo formalizations when get embedded on a quantum annealer solver, like for example, let's say you took Fujitsu or let's say D-Wave, you need a specific chain strength. So how are you figuring that out, or are you leaving that up to D-Wave? Because in our experience, we have found out that's the biggest culprit in terms of reducing a qubit size and degree of freedom.
So I don't know if I understood you correctly. So you're saying that the D-Wave machine doesn't have like a full connectivity, yes?
Correct. So
Yeah.
D-Wave uses something known as an embedding composite.
Yes.
So
Yeah,
that
you are
takes up a
right.
lot of qubits.
Yeah, you are right. To like encode a fully connected graph on the wave machine, you reduce the number of qubits substantially. So yes, you are right. This is the one of the main problems when using D-Wave. So, but as I said before, we are experimenting with D-Wave, but we also do we have our own solver. And then we actually are able to perform all-to-all connectivity for this one.
Makes sense, right?
And we use it. I will maybe just find an archive number for this one. So for the solver, the solver is called LXVII, and this is actually what we are working on, what we at the company Quantum.io is made, so we can take a look at it, and it actually provides a solution at larger problems we can embed in, because it can run on a fully connected graph, and it works better actually with less less noise than the D-Wave solution.
Also one very quick follow-up, if that's okay. Why haven't you so I believe that it must come up, but wouldn't exploring things like the Markowitz formalization, which do not require all connected graphs, or something like the Braviki type transformation would work better for a structure size where you need a higher range of data, because then effectively you're using much less qubits in terms of your transcribing instead of an all-to-all QBO conversion?
Yes, you're right. So you are right that we can utilize it, but as I mentioned, since we at the moment we mostly use this VelocQ implementation, we didn't consider it. So actually, what we are waiting that this D-Wave machine will be, let's say, it will become better, and we will be able to encode bigger problems on it and with full connectivity, hopefully. So we didn't consider it at the moment, but thanks for suggestion.
Perfect. Thank you so much again for the talk and the questions.
Thank you.
All right, thank you. Thanks for sharing the link. Do we have more questions or comments? All right, I don't see more questions now. Zbigniew, thank you once again for a great presentation and for answering all the questions on the fly and now. Maybe I'll just present a few last slides at the end just to invite people to the next meetup and show some links. All right, there it is. And the slides. Okay. Oh, yep. Can you see my slides again? Hope so. All right. So we thank all of you for attending and for attention, of course. Let's stay in touch. If you're interested in our events, you can follow our profiles on social media, our YouTube channel. Hopefully, we'll upload the video recording in about 2-3 weeks. And you can join our Discord server, our mailing list, and subscribe to our monthly newsletter. We would like to thank once again our strategic partners. So first of all, QuantumZ.io was the main partner, and as you know, Zbigniew was also talking about the project related to QuantumZ.io. So Novero R&D, Onyx, Cogit, AIQ Lab, and InQubit. And we also thank our honorary partners. If you like our activities, you can also donate, especially if you are in Poland, there are such options. And we would like to invite you to our next episode, episode 68. Most likely it will be in about 2 weeks from now, May 28th, and we are planning it to be an on-site event in Warsaw this time. We'll hope to announce it soon. There will be a nice, very good speaker from abroad coming to Warsaw. So stay tuned. We are going to announce the next meetup within the next few days. All right. Thanks once again. I will now stop sharing my slides and I will also stop recording.